Enzyme inhibition is something that's new at AS. You don't really cover it previously. And it's another way of understanding this whole interaction between enzyme and substrate and things that can impact on it, because of course life is far more complicated than how we study it. It's really important that you get a good grip on inhibition, because it's very much a case of understanding what's going on so that you can then apply it in questions. Enzyme inhibition questions are often applied questions. So we're going to look at it slightly differently in this lesson. We're going to look at it visually to start with. So let us set up with some enzymes. We're going to have 3 enzymes. But I want them to look a little bit prettier than that. There we go. So each of these is an enzyme. Now this first enzyme, we're going to give him his substrate, okay? So there's a substrate, and it's going to be a one that's breaking down, okay? So we're breaking big triangle into 2 little triangles. Nothing wrong with simplifying a reaction to shapes. Okay, so now here we have enzyme plus substrate goes to products. When it comes to inhibition, now something different is going on. Okay, and there's 2 different places where an inhibitor can bind, or 2 different groups of places. First one is the inhibitor could bind at the active site. Okay, so the active site is a little mouth in our enzyme in this diagram. So let's bring along an inhibitor. Now it's got to have a complementary shape to that active site, okay? But he's not the same as a substrate. So maybe he's different on the other side, okay? Now what's going to happen here is we're going to have an enzyme. Oh, we missed a bit on the last one, didn't we? Okay, we had product plus our enzyme is unchanged and ready to go. Okay, so now we have an enzyme, but he's not unchanged and ready to go because he is bound to the inhibitor. So now we have enzyme plus inhibitor has gone to an enzyme inhibitor complex. So now it doesn't matter if our little pink pink substrate comes along, the inhibitor is in the way. He's blocked that enzyme, taken it out of action. Okay, so what happens if we have a different kind of inhibitor? What happens if our inhibitor looks like this? No, that's not complementary to the active site. Okay, but this other place where an inhibitor can bind is somewhere else on the enzyme molecule. Okay, so let's say this inhibitor binds down here. Okay, but now whenever we bind something to a protein, we're going to disrupt other bonds within the protein. We're going to change its shape. So now our enzyme is going to look something along the lines of, in our imaginary world, that. Just neaten that up a bit. Okay. And now, if our pink substrate comes along, there is no functional active site. Okay, so we've split here between our very normal reaction at the top. With our enzyme plus substrate goes to product plus enzyme. We're ready to go again with the next one. Okay, that enzyme is reusable. It nothing happens to it during a reaction, so we just keep going. In these other two options, we have enzyme plus inhibitor, and that creates an enzyme inhibitor complex, and it effectively takes that enzyme out of action. These are completely dysfunctional enzymes. So the enzymes don't function. So this is how inhibition happens, okay? Either we block the active site, like our orange inhibitor, or we bind somewhere else on the molecule and we then distort the active site, like our red inhibitor. In either case, our substrate can't connect with the enzyme, and therefore the enzyme can't do its job. Because enzyme inhibition is all about reducing the rate of the reaction. Because remember, enzymes are all about increasing the rate of the reaction. So if we take enzymes out of play, the effect is to reduce the rate of the reaction. So there's all sorts of other terminology which we now need to pull in now that we're happy with this. So we're going to first talk about competitive inhibitors. So competitive, competing. Okay, so some way this inhibitor is competing with something, and what it's competing with is the substrate itself. Okay, so a competitive inhibitor is one that has a similar shape to the substrate. In particular, the piece that must be very similar to the substrate is that it must be complementary to the active site. So the inhibitor is complementary to the enzyme's active site. So if we have a look at our visual one, you can see straight away the inhibitor that is the competitive inhibitor is our orange one, because he has got that same pointy bit that fits into the mouth of our enzyme. Okay, so the shape of the substrate, the shape of the inhibitor, both of those are complementary to the enzyme active site. So we're complementary to the active site. The other thing that we have with competitive inhibitors is that they make temporary bonds. So temporary bonds to active site. Now that sounds exactly the same as when our substrate bonds. So also hydrogen bonds. And of course, that means that our competitive inhibitor is reversible. So our inhibitor goes in, it bonds, but it's hydrogen bonds so that they break and then the inhibitor's out, now the enzyme's free again. So competitive inhibition, in order for the inhibitor and the substrate to compete, the thing that's got to happen is that they've got to be created equal. If they are not the same in terms of how they're interacting with the enzyme, then they're not going to be able to compete. Okay, so competitive inhibitor must be the similar shape to the substrate so that it is complementary to the active site, and you must have those temporary bonds so that the inhibition is reversible. So last thing, reversible inhibition. In this case, then we would have a competitive inhibitor, and it would be a game of numbers. Do my inhibitors take up my enzymes, or do my substrates take up my enzymes, depending on the relative frequencies of the two. Where things get more interesting is when we get into then non-competitive inhibition. So non-competitive inhibition, something is different now between our substrate and our inhibitor so that they don't compete with each other. Okay? But we still have reversible and irreversible. So we're going to consider them separately. Reversible and irreversible. So if we think about non-competitive, we go back to our pictures here. Non-competitive could actually be each of these. Okay, so let's take our orange inhibitor. We've said now for competitive, we make hydrogen bonds, it's temporary, and it's finished, okay? It comes out again and there's no effect. If those bonds were permanent, then we have a problem because now we're not competing anymore. Our inhibitor and our substrate are not equal. So for non-competitive inhibition, we would have permanent bonds in this case, or we could have this situation where our inhibitor is bound somewhere else. So he doesn't care about the active site, he binds somewhere else. So he's not competing with that substrate. Okay, so if we then go back and consider our non-competitive inhibition. If it is reversible, it has to be bonding somewhere else. Okay, because if it was bonding reversibly in an active site, then we'd be competitive. So it's bonding elsewhere, but in order to be reversible, it must be temporary bonds. Okay, if it's irreversible, it could be bonding at that active site or somewhere else, because the thing about being irreversible is that it's a permanent bond. So the question has come through about what happens to the inhibitor when it leaves. So if we've got a temporary bond between our inhibitor and our enzyme, what happens when that bond is broken? And nothing happens, okay? So it's only the substrate that would be broken into product. When it's an inhibitor, it's just stopping function. So the inhibitor also remains unchanged by this interaction. So now we've got this whole concept of where are we bonding and what type of bonds have we got? Are they temporary or permanent? Are we binding in the active site or elsewhere? And are we reversible or not? So we're actually going to now put all of this into one table, another way of looking at it. So I think we're going to rather make more space though to do this. Making comparative tables is a great way for learning things and studying in biology, because there's a lot of information to synthesize and get a hold of. And sometimes when you put things into a table, it can help organize the information, and that makes it stick a lot better in your head. Promise these are beautiful lines. Okay, so the information that we want to put in. We've got competitive. We've got the binding site. So let's just call it the inhibitor binding site. The type of bond and the reversibility. So the permanence of this. Reversibility. Okay, so competitive, and then we actually have all our variation in the non-competitive. I am spelling very badly this morning, aren't I? Spelling is important. Competitive. There we go. Competitive. And non-competitive. Goodness gracious, that's not a word to write over and over again. Right, so now we're going to take all that information. So when we talk about a competitive, I spelled the first one wrong as well. Competitive inhibitor, where does it bind? If it's going to compete, it must be just like the substrate. So it's got to bind at the active site. The type of bond has to be temporary because that is the same as a substrate, and it has to be reversible. We have to be able to be exactly like a substrate. Enter, bind, leave. So a competitive inhibitor works in the same way as a substrate. The only difference is not being broken down into products. It's remaining unchanged when it's released. For a non-competitive, let's say that we are bonding elsewhere. So not in the active site. If we then have a temporary bond, we have another reversible inhibition. Okay, because it's temporary. So it's not competitive because we're not looking for the active site, the inhibitor and the substrate. The inhibitor is looking for some other piece of the enzyme that it's going to bind to, but it's temporary and therefore it's reversible. So it is something that can be reversed. If we now look at the other two, let's say it's non-competitive binding at the active site. Okay, but in this case, it's a permanent bond. So it's not a case of competing anymore, because once that inhibitor is in that active site, that enzyme is taken out for good, finished, over. Permanently bonded to an inhibitor, that active site is never going to be available for another substrate. So this one now is irreversible. So our last one, of course, is going to be elsewhere again. So we're bound somewhere else on the enzyme, not in the active site, but again with permanent bonds. And when we have permanent bonds, that enzyme is taken out. That active site is deformed forever now. So it is irreversible. Okay, so we've got now an idea that non-competitive is a lot more varied than competitive, because competitive inhibition has to be just like the substrate. Have we got any questions at this stage? So if we think about what type of bonds these permanent bonds will be, it's anything stronger than a hydrogen bond. So we're looking at things like disulfide bridges. So we're actually making a permanent bond more on the line of our covalent bonds, so that non-competitive is stuck in there. It's not just going to bounce out again. So if we take it back here, we can now say this one is giving us a bit of an example of, let's find a color we haven't used. This is turning into a rainbow, this page. Okay, we'll go for the pale blue again, rather. So this one could be competitive, or it could be non-competitive, depending on the permanence of these bonds. This one is always non-competitive, because there's not equal footing between the substrate and the inhibitor. Okay, so reversibility again, either of these could be reversible or irreversible, depending if we've got temporary or permanent bonds. So the last place that we want to take inhibition is thinking, right, so what is the effect of changing substrate concentration? Because that is a lovely little graph that they like to play with. So let us now consider the effect of substrate concentration. I need to practice using these, so let's do it now. See, it is possible to get straight lines. Brilliant. Okay, so let us have a few different lines here. We've got that one. And we'll do one that goes like this. And we shall do one last one that goes like this. Okay, so any ideas as to what's going on our axes? Of course, this is looking at enzymes. So we're going to have rate of reaction on our vertical axis. Okay, so if it's an actual experiment, it would be rate of bubble production or something like that. And down here, it's the effective substrate concentration. So down here would have to be substrate concentration. Then we've got our 3 different lines. So in pink is your classic, okay? No inhibitor. So as substrate concentration increases, so does rate of reaction until we get to Vmax, where all the enzymes are working at their maximum velocity, and there we stay. That is the maximum rate of this reaction that we can get, unless, of course, we increase our enzyme concentration. Then we can get a faster rate. Okay, so no inhibitor in pink. So these in orange and red, these are our 2 options, competitive and non-competitive. And figuring out which one is which, we've got to think, okay, so if we have an effect that is changing with substrate concentration, like our orange one, or an effect that is not, gets to a point where there is no effect, what's the difference? The difference is that one of these we have competition and the other one we don't. When substrate concentration is really high, then we're getting a higher rate of reaction. This must be a competitive inhibitor. Because effectively, at these very high substrate concentrations, it is outcompeted. So substrate outcompetes inhibitor at high concentrations. So we've got this idea that the more substrates we have, then the more likely that enzyme is to bump into a substrate. So this is why we get this nice straight line, because effectively it's a one-on-one relationship. That, remember, our inhibitor concentration at this stage is staying constant. So we'll get to a point where we have sort of 50-50 inhibitor and substrate, and then the substrate is going to start overtaking. And we just keep on going up until we potentially reach that full rate of reaction where we have so much substrate that the inhibitor is a negligible amount. So the probability of hitting a substrate is vastly outweighing the probability of hitting an inhibitor. When it then comes to this other red line, this then, of course, by a process of elimination, is our non-competitive inhibitor. And the thing here is we have the same graph as our no inhibitor graph. Because what we've effectively done is that the inhibitors have taken the enzymes out of action. So the number of inhibitors has effectively reduced our enzyme concentration. So we have reached an effective maximum velocity at a much lower rate of reaction because we effectively have less enzymes. Because that inhibitor is not competing with the substrate, it doesn't matter how much the substrate concentration is increased. Once that sort of portion of enzymes is taken out, it's finished. It's gone. They're not going to work, there's no competition, and that is then the enzymes that are out, and we're left with what enzymes are left to do their job. And that is then giving us that lower maximum rate of reaction. So make sure you understand your competitive and your non-competitive, and then how that links in also between different bonding types and then permanence of the inhibition. And then it all plays together in understanding what the inhibitor is doing to the enzyme and what it's doing in the reaction situation. So if you don't get this, then make sure you go back and go through it all again, because it is a question that they really like to use for applied work. So it's well worth getting a good grip on enzyme inhibition.